Okay, so this is a video by Physics Girl. I'll pause this for just a second. I love her videos because I'm a nerd. But in this one, he's gonna look at different kinds of sunscreen and how they absorb ultraviolet light. So what she's gonna do is the black and white scenes are gonna be where they're looking at her with an ultraviolet camera. So basically, they're taking any ultraviolet light that hits the lens of the camera and then changing it to visible light so we can see what is there. So when the sunscreen is absorbing the ultraviolet light, then we'll see black because it's not being reflected off. So that it's generally a good thing when we see that absorption. And so she's going to look at various SPFs. SPF, that's one of the questions on the last page of your guided notes. SPF is what? Sun protection factor. Okay. The idea of an SPF is that if I have an SPF of 2, I can stay in the sun twice as long as if I didn't have that. If I have an SPF of 15, I can stay in the sun 15 times as long, and so forth. So even an SPF of 10 is blocking about 90% of the radiation, the ultraviolet radiation from the sun. So that's good. If you're fair skinned like I am, that doesn't mean that you're necessarily going to be protected from sunburns for very long. Also, people tend to put a lot less sunscreen on than they're supposed to. They say for your face, you should take 2 fingers, cover them with sunscreen, and use that much to cover your face. Most people will take a dab or 2 and just kind of pat it around. So generally, even if you're using like SPF 70, you're not getting that kind of protection. I think this one's a longer one, so I'm gonna kind of jump forward in certain spots through it. The other thing I want to say about Physics Girl is that she was hit really hard with COVID. She's very active and was a runner and those kinds of things, and she got engaged around that time. And she ended up having long COVID, and for about a year and a half, literally couldn't get out of bed, like physically was not able to get out of bed. If her fiance, and then they ended up getting married, her husband brought in any food into the room, she couldn't tolerate it. And so she was basically living on water and the minimal amounts of broth and things for about a year and a half. This is a pretty rare condition, but it is something that does happen. And so when you hear people talk about this, a lot of times people say, oh, that's not real. And they don't believe that it's happening. It really is real. And so this is her here, in a lot of pain and agony. She had to cut all of her hair off. And she's just slowly getting back to the point now where she can stand, she can walk, she can go around, that kind of thing. Some people have the condition for a lot longer than she did. So compassion is the big.
It's right there. Okay, but you're not needed for this video yet, so you just chill. So a couple months ago, a few guys got in touch with me and told me that they had access to a UV camera. Do you know what that is?
Yes.
Basically, it's a camera that allows you to see the world in ultraviolet, which meant a few things for me. It meant that I could see what this looks like in UV. I could see what your face looks like without any lotion or makeup on in UV. And I could see how sunscreen shows up on your face in ultraviolet. And so I said, yes, please do come visit me in San Diego and bring your UV camera. And so the guys from the very well-made YouTube channel, How to Make Everything, showed up at my house. This is what we did.
Yeah, on your pants. Your pants are so tight right now.
Grammarly doesn't just help you with polishing your emails, it also lessens the mental load of replying to emails.
You have some weird tan lines after this.
I was just thinking that.
This is so crazy.
Those are dental ones.
Okay, so the dark spots that you see here, that's where they put sunscreen on him. And when she moves out of the way, you're going to be able to see, just like with normal sunscreen, you can't really tell.
Bigger the better. Yes, me. Whoa! I gotta see this.
Is that showing up?
Oh, yeah.
Can finish it. But for this video, we're gonna cut in a few times to discuss the sunscreen controversies.
There are a lot of misconceptions about sunscreens, and we're going to clear them up.
Yeah. But for now, I'm gonna turn it over to Diana in the studio.
Back to you, Diana.
The first thing I wanted to look into was whether different SPFs, that is sun protection factor, which actually is supposed to indicate how strong the sunscreen is. But anyways, I wanted to see whether different SPFs of sunscreen look different under UV light. And then I wanted to compare whether high SPFs like SPF 100 are more effective than just regular high SPFs like SPF 50. Here was my thinking. With a UV camera, things that look lighter are emitting or reflecting UV light, like the wall behind us. And things that look darker, like the shirt that I'm wearing, are absorbing UV light, which is something that I think you'd want to know when it comes to sunscreen, because UV light, ultraviolet light, of course, is part of the spectrum of light or electromagnetic waves from the sun. And UV is just on the far side of the violet part of the visible light rainbow, which means it's a wave that has a shorter wavelength, which means it has a higher frequency than any visible light. And in the end, it can do more damage to molecules like DNA or to cells. And as we all know, it's been linked to skin cancer. So my thinking was that if you look at your skin with sunscreen on, you should see that UV light is absorbed. So it should look darker. And yeah, like when we put the sunscreen on, it looked like face paint. We were even able to graffiti the side of the truck with sunscreen, but of course you can only see it with the UV camera. So my hypothesis was that the sunscreen with the highest SPF should look darker with the UV camera. And so we tested a bunch of different sunscreens with different SPFs on a grid on my arm, drawn with permanent marker. Here's what we saw. So you can't see anything.
That's just so
Wow. It looks like paint.
Yeah.
It looks like metallic black paint. Initially, we saw that, yeah, the low SPF areas do look less dark. You can tell they don't seem to be absorbing as much ultraviolet light. But interestingly, there's not a ton of difference between the 30 to 110 SPFs. And I've heard this rumor that SPFs above 50, anything really high, doesn't actually do anything more than SPF 50. So I looked into the scientific literature on this, and I actually found a study that came out just this year in May 2018 that tested 199 people with SPF 50 and SPF 100 sunscreens. Over the course of about 6 hours of sun exposure, the subjects got more sunburnt with the SPF 50. But they
Okay, so she's looking into the scientific literature, 199 people. What do we call that? The sample size. She had a sample size. And they are looking at sun exposure. Everybody is getting the same amount of time in the sun. So is that a variable? No, that's a control. If it's the same for everyone. What's different between the people that the scientists are controlling? The SPF. So the scientists control the, which one? Independent or dependent? Independent. The independent variable is the different types of sunscreen, and the dependent variable is how much sunburn.
put a nice little disclaimer at the bottom of the paper that leads you to conclude that more research needs to be done on whether there are more benefits over the long term of using SPF 100 versus 50. Hey guys, I just want to pause on this for a second because I still think it's weird that I had this conception that above SPF 50 you don't get any more benefits. And Derek, let me know what you think about this. But I think I've figured out where that conception came from. And I think that it's from a 2011 proposed rule from the FDA, the American Federal Drug Administration. Yeah, they proposed a rule that would limit the maximum allowed SPF labeling to 50 plus. Thoughts?
I also don't think it's strange, the conception that the high number sunscreens are all basically equivalent. You know, when I lived in Australia, people were limited to putting only 30 plus on the sunscreen bottles, and now they've moved that up to 50 plus. But it's still, I think, a good idea because as those numbers increase, you're getting kind of diminishing returns. So what's the difference between 50 and 100? Well, it's not really that much because a lot of how effective they are comes down to how much you apply and how well you apply it. So, you know, I think it's just a marketing gimmick to say that like this is a 75 or this is an 80 or this is a 90.
So obviously SPF and the efficacy of different sun protection factors is still an active area of research.
50 lets in 2% of the ultraviolet light. 100 lets in 1%. That's the difference in the amount of light that is in. 2% versus 1%. So that's where people say, well, the efficacy of that is not a lot. It still is protecting you more. It's just not a lot. But you do have a benefit for having higher levels. Okay, the other thing I wanted to look at, I think, was this one right here, where it was a different kind of sunscreen. So remember, most of the sunscreens looked very black. This one is a little bit different.
Fun day at hand. When we were looking at the sunscreens with the different SPFs, we tried a different sunscreen with SPF 25 and something weird happened. It was actually lighter, like really light. This means that it's not absorbing UV light, but could it still be sunscreening? Yes, if it reflects UV light, which is most likely what's happening here with this sunscreen that has zinc oxide in it, which is a substance that's known to reflect some types of UV light. So, this is where I got really confused. I started looking up some sunscreen ingredients and what they do and why some are reflective and others are absorptive, and I ended up going down the rabbit hole of sunscreen controversies. I'll get to the discussion on health effects of different sunscreen ingredients in a minute. But I did find that Hawaii recently banned some sunscreens from the state. The reason why is that the ingredients oxybenzone and octinoxate.
All right, so on your guided notes, identify 2 specific compounds that may be used to prevent the overexposure to sunlight. I wonder where you could find 2 compounds that might be in sunscreens. And then the other one she mentioned was zinc oxide. If you've seen movies from like the 90s where people are at the beach and somebody has like white or blue or pink on their nose, they used to have like a piece of zinc oxide. So they would just literally get like, it'd be like white powder, mix it with, whatever lotion, and then you put that on your nose and it'd be like, oh, I have a shirt on my nose. It's preventing me from sunscreen. Now they break that down into what are called nanoparticles. So it's like powderizing the powder to teeny tiny particles. And they're so small that when you mix it with the lotion, then the light can still get through, the regular light can still get through. So it doesn't look like you're wearing this big pink or blue or white thing on your nose. It's just regular sunscreen. But back to this, why doesn't Hawaii want these? And I went with my family on a cruise to the Caribbean last year, and they wouldn't let certain kinds of sunscreen on for this reason as well.
Were found to be contributing to coral reef bleaching, a process whereby coral polyps expel the little algae.
So see how this coral is kind of orange, and in the background you can see some red and some green. Coral is usually very vibrantly colored. And so if we look back here, that's all very white. That's basically right before the coral dies. Okay, so imagine if in the middle of the summer, somebody came and took all the leaves off the tree. The tree's still alive, but if you take the leaves off, it can't do photosynthesis anymore. And it's not the winter, so it's not in its dormant stage. It's going to start to die. That's what's happening with a coral reef sea. Okay.
Process whereby coral polyps expel the little algae living inside of them. Actually kind of sounds like an exorcism, but it is in fact a bad thing. So starting in 2021, Hawaii is banning any sunscreens with those ingredients. This ban was based off of recent research.
All right, so that's all I'm going to do with that one. If you're a science nerd like me, you might want to watch the rest of it. The link is in the PowerPoint, but we're not going to watch the rest of that right now. Okay. So, who ends up getting skin cancer? Like most health conditions, it's not just across the board. Everybody is equally likely to get skin cancer. What we find is that unlike most health conditions, this is a case where white people lose out. So in most cases, having lighter colored skin is connected to some of the benefits in society that lead to less stress and more wealth and things like that. So there's all kinds of socioeconomic things that make the differences between races or whatever. But in the case of skin cancer, having darker skin at your birth means you've already got that melanin that's protecting. You don't need to damage your skin to produce it. So, one of the editions of the book had this broken down a lot further, but I couldn't find the image digitally to put here. So this one just has black versus white. And so this is going from 1975 up to 2015. So about 40 years. And what's the trend for this red line? Increasing. Yeah, that's white people. Cases of skin cancer are increasing. Now, people end up getting skin cancer decades after they were exposed to it. So this is really telling us about what was going on more like from, say, the 30s and 40s onward. So as we're going through the 50s and 60s, more people were going out in the sun. There was more wealth, so people had more leisure time. They could go to beaches. Tanning was becoming more popular. So lots of increases across the board there. But for Black people, as a general rule, you can kind of see it's even going down a little bit. So we do have some differences there. There is an activity that you are going to end up doing. Did I not put that on there? Oh, that should have been on there too. People and light. So that's a second assignment that is on Canvas. And it's going to link to data like this. And it's basically going to ask you to plug in your own data. How old are you? What race are you? Do you have a Hispanic background? And look at what is your risk of developing skin cancer. Now, unfortunately, it's what's your chance of developing skin cancer right now, not in your lifetime. So what you're going to see is that for all of you, because you're very young, it's going to be very low. But you are going to see differences when you start comparing yourself to the general population. Okay, so you'll be able to see what is it, my risk, what is the risk of women versus men. So if I'm a female, am I more likely than a man? So on and so forth. All right, so I mentioned eyes. You probably have all heard of cataracts. I learned last night I was playing Connections. It's one of those word games. A cataract is also some kind of a water current. I don't know what it is, but it was listed with water currents. But it is also refers to a cloudiness that develops in the eyes. See, that's kind of shaded. And so instead of the light coming to a sharp focus at the back of the eye, it sort of gets dispersed out. So think of light coming to you through a fog instead of having nice sharp images and sharp shadows on the ground. Everything is kind of fuzzy and cloudy. And so colors aren't as bright and everything looks a little bit cloudy. And so that is connected to ultraviolet radiation. Like I said, it does kind of depend on your age, and also other factors may be involved as well. And then finally, vitamin D. This is produced in the skin. And so what we're looking at here, this says personal exposure to UV radiation. So going across, we have low versus high exposure. So here I'm living in a cave and I never see the sun. Here I'm out in the sun all the time. And then this is your disease burden, so your likeliness of being ill. And this is from all diseases, not one particular one. And so basically this is showing you that if you get no sunlight, your problem is vitamin D insufficiency, which leads to skeletal disease. So vitamin D is called calciferol. So it has calcium kind of in the name. Vitamin D helps our body to take that calcium that we eat and put it into our bones. So it makes stronger bones. So if you don't have enough vitamin D, you can have a skeletal disease. And so if you look up, rickets is a disease that's associated with this, particularly for young children as they're growing. They're load-bearing bones in their legs, so they have a lot of weight on them. As they are growing, those bones start to bend because there's so much weight on them compared to the strength of the bone. And so sometimes they end up not being able to walk at all, or they always walk very strangely. Their legs are built very strangely because of this vitamin D insufficiency. So we don't want to never be in the sun, but if we're always in the sun, then of course we have some problems. All right, so light is good in small doses. Ozone is good up high, but not so much close to us. So this is kind of a zoom in on that sideways graph that we had. In the ozone layer, remember, we are in the troposphere. Our tallest mountains are about here. So I think this is like Everest would be about this high. So we got another 5 kilometers between the top of Everest and our peak ozone layer area. So down here where we're living and breathing, it's not hurting our lungs because it's very low, but notice that it comes out again very, very close to the surface because we're creating pollution. So ozone is increased from pollution. We don't want that damages our lungs, but way up here, it's absorbing ultraviolet light. Okay. All right, you do need to know some differences between ozone and oxygen. So we talked about the formula, O2 versus O3. There's an odor difference. We can't tell the smell of oxygen because it just smells like air. But ozone has a very distinctive smell that can be very sharp when it's in high concentrations. So there's a difference there. Oxygen, O2, has very strong bonds. So if you go in here to question 14, it says, which of the above molecules are very reactive? O3 is very reactive because it has a weak bond. And then in question 15, which are very stable? O2 is stable because it has a double bond, which is stronger. And even more stable than that is CO2. CO2 is probably the most stable of those. CO2 and H2O are very stable because they have strong bonds. So ozone, good thing. We've all heard of the ozone layer. It's gotten less attention recently, but when I was growing up, the whole thing was like, oh no, there's a hole in the ozone layer. So this is mostly stuff we talked about in the last slides. Depending on the type of light, energy, it can affect molecules in different ways. And so UV can break apart some molecules. Microwaves, they're a kind of light. They cause molecules to rotate, and infrared causes them to wiggle, to vibrate. So if you have your Canvas app or your tablet with you or something, you want to go to the activity that is on the board here, light interacts with molecules. So this link here is the one that I'm showing you. You don't need to click on that. So it says, what's the chemical symbol for ozone? So what letters and numbers do we use for ozone? O3. And it says how many red balls are shown in the drawing. And so let me go back to the drawing to see it. There are 3 of them. And then it's going to ask you what happens when different kinds of light hit the molecule. So these waves going by are supposed to be the light hitting the molecule. And right now our black box is right in the middle of visible. And so it's gone through the molecule a few times and nothing much has changed with visible light. Now we know that there are some electrons moving around in there a little bit, but mostly it just doesn't change. There's really no effect. Now, if we go into ultraviolet light, we have UVA, UVB, and UVC. So let's wait for the wave to hit this with UVA. Any difference there with UVA? Not really, okay? So the ozone doesn't do too much to UVA. We go to UVB, what happens? Popped up, so let me get it back there. Wait for a wave to come through. It breaks apart. Okay, so UVB, it breaks apart. Let's see what happens with UVC. It breaks apart. Okay. So, and I should do that on here as well. There's UVA, UVB, and UVC. Okay, now we can also look in the other direction. So if we take it down, is the next question microwaves? I think it's microwaves. If we move this black box down to microwaves and watch what happens. What's happening to the molecule? It starts spinning. So if we can imagine a bunch of different molecules in our food, when they're hit by a microwave and they start to try and spin, they're going to bump into each other. And as they bump into each other, that's what's creating the heat in our food. The microwave is causing it to spin. Infrared, we're going to see. Starts wiggling like crazy, right? It vibrates faster. That's going to be important for the next chapter. All right, and for completion, here's radio waves. Not much going on with radio waves. X-rays. So like I said, we can break apart the molecule with the X-rays. And gamma rays even higher energy. Notice what's happening to the wave below the spectrum as we move it around. The wavelengths are changing. Gamma rays breaks that apart too. So gamma rays have the highest frequency. And as we move down, radio waves have the lowest frequency, the longest wavelength. Okay, I want to do the next slide real quick. And then we will pause for the weekend. Okay, so in the 20th century, a lot of innovation happened. And one guy did a lot of it. So we had cars at the very beginning of the 20th century. Before the 1920s, it was exclusive to the really rich. They were loud, obnoxious. They produced a lot of smoke and stuff. And then this guy, Thomas Midgley, created tetraethyl lead. So ethyl, how many carbons? 2 carbons, right? And tetra means 4. So there were 4 groups of 2 carbons attached to this, and that caused the knocking to go down. So this guy is the reason we had leaded gasoline for so long that caused lead to go up in the atmosphere. Now, he didn't know that was bad at the time. He did that in the early 1920s. Around the same time, we got refrigerators. Now, if you ever hear like grandma refer to it as an ice box, they used to like actually bring around a block of ice, put it in the bottom of this box, and then you'd have your food sitting above it, and that would be your ice box. So refrigerators, as we know them, were pretty uncommon, and they used toxic gases. We'll talk about those later. In the 1930s, Freon replaced those toxic gases. This guy, again, created those gases. Those were again used in air conditioners. In the 30s, it was exclusively the rich that used them. By the 1950s, more prosperity, it became the everyone used them, and it allowed people to move further south because places were air conditioned. The problem with those was that Freon is a chlorofluorocarbon. So it tells you the 3 elements that are in there: carbon, chlorine, and fluorine. It was used because it was not toxic, so that was great. It was not flammable, that was great. It was cheap, and it was chemically stable. So it was used in refrigerators, in air conditioners, and also used as a propellant for sprays. But as you may know, it is the main culprit behind the thinning of the ozone. Okay, so we'll talk more about CFCs on Monday.